film on the F2H2 Banshee will cover taxiing, takeoff and climb, normal flight, maneuvers, single engine flight, approach and landing, and securing. The F2H2 taxiing or idling on both engines for 1 hour will burn over 280 gallons without going anywhere. Jet pilots want this fuel for flight reserve. Maneuvering on the ground, therefore, should be kept at a minimum once the engines are started. Visibility from the cockpit is very good. On flat, hard surfaces, the airplane will roll with tricycle landing gear. It is safe to taxi at fairly high speeds. So, if the taxi strip is clear, let the airplane roll freely, using the brakes for steering only. The nose wheel swivels freely through 360 degrees, but is not steerable. There is no stick or rudder control at taxiing speeds. The airplane handles well in crosswinds. To save the brakes, balance the wind force with unequal engine RPM. Stay on the runway because on soft ground, the high loading on the tires lets the airplane bog down very easily. In turning, you may use the engines to help the brakes. Because of the slower jet response, you'll need to anticipate your power requirement. To save time, the takeoff checklist should be combined with taxiing. Shoulder harness locked. Wings spread and locked. For field takeoff, flaps 1/4 to 1/2 down. Controls free. Pop the speed brakes on and off. Canopy open. Trim tabs at 0. Check aileron boost switches on. And check aileron movements for full throw. Check auxiliary fuel transfer switch as desired. Test the yaw stabilizer by holding the switch in test position. Make slight S-turns when taxiing. The rudder pedal movement should be opposite to the direction of the turn. Turn the yaw stabilizer switch off and leave it off till safely airborne. Do not take off with unbalanced loads in external auxiliary fuel tanks. We have completed the takeoff checklist. When you make the turn into takeoff position, remember that with the tricycle landing gear, the airplane responds better if it is rolling before the turn is started. After the turn, taxi the airplane ahead a few feet to get the nose wheel lined up. Apply the brakes and advance the throttles. Here are the desired readings. RPM 100%. Tailpipe temperature 625 degrees to 660. Oil pressure 60 to 90 psi. Release the brakes. The airplane will pick up speed slowly at first. The pilot has excellent visibility. There is no engine torque, so steering is no problem. There is no response to the rudder below 60 knots, so all steering is done with the brakes, which are quite responsive. Between 80 and 90 knots, a little back pressure on the control stick will lift the nose wheel off the ground. The takeoff run seems long to a reciprocating engine pilot, but seems short to pilots accustomed to other jets. The Banshee takes off at about 105 knots, and once airborne, the acceleration is rapid. Get the landing gear up and turn the yaw stabilizer on as soon as safely airborne. Hold speed in the climb below 165 knots to a safe altitude of 200 to 300 feet when you raise the flaps. As the flaps come up, the stick will automatically come back an inch or so. Hold the nose down to get the best climbing speed. For climb to altitudes, the throttle setting should be left at 100% of RPM, and the climbing speed at sea level should be approximately 305 knots indicated airspeed. Climb speed should be reduced about 10 knots for each 10,000 feet of altitude. In climbs, both two-engine and single-engine, the use of military power saves fuel in reaching desired altitude. The normal flight characteristics of the aircraft are excellent. The combination of aileron boost and yaw stabilization makes for very smooth flying. The stalling speed of the airplane will vary considerably with the fuel load. With gear and flaps up, there is a natural warning consisting of an airframe buffet, 3 or 4 knots above the stall. The stall is mild and may be broken by forward stick with very little loss of altitude. Ailerons and rudder remain effective throughout the stall. In the accelerated stall, there is even more warning from airframe and elevator buffet. Aileron and rudder controls are effective. Power has little effect on the stall except for a slight decrease in the stalling speed. With gear and flaps down, there is little natural warning. An artificial warning or stick shaker has been provided for a speed approximately 7 knots above the stall. The initial stall is mild with good aileron control, and recovery is immediate with a small altitude loss if the stick is pushed forward. With gear and flaps down, the accelerated stall gives reasonable buffet warning. The airplane will recover immediately if stick is eased forward. With gear and flaps down, the airplane may go into a fully developed stall if proper recovery measures are not taken. The elevator buffets sharply, losing most of its effectiveness. Aileron and rudder control are lost. In some cases, the airplane will mush 400 or 500 feet nose high before breaking the stall, or may roll sharply either left or right into a vertical descent, requiring as much as 1,500 feet of altitude for recovery. Power on aggravates this fully developed stall condition. The airplane is restricted against practice spins. However, it is important to know its spin characteristics. Entry to a spin is slow. With the nose high, the airplane rolls mildly in the direction of applied rudder as the nose drops. If control forces are held, the airplane will enter a 1/2 to 3/4 turn spin at a moderate rate, with the nose down to approximately vertical. Auto rotation then practically stops and the nose rises sharply. At this point, center control. Let's watch a spin in slow motion. Here is the stall. Nose down and into the spin. The nose rises. Recovery should be made now. If the control forces are held to keep the plane in a spin, the nose drops steeply. This cycle continues approximately once per turn with an altitude loss of approximately 2,000 feet per turn. The nose up pitching and whipping back into the spin becomes increasingly more violent for the first 2 or 3 turns and then remains constant. If recovery occurs during the nose down part of the spin, approximately 3,000 feet of altitude will be required for recovery. In any case, recovery from normal spins is affected by centering the controls. Inverted spins are quite delayed in entry. The airplane enters with a roll in the direction of the applied rudder and the spin is slow and uniform. Recovery normal with full opposite rudder followed by back stick. Let's watch the Banshee run through her permissible maneuvers. Steep dive angles may be used without exceeding the limits of the airplane. Airspeed can easily be controlled using throttle and speed brakes. When the speed brakes are open at speeds above 0.78 Mach, there is a slight nose-up tendency which is increasingly stronger at higher speeds. Engine speed is governed so it does not increase appreciably in dives. On completing a dive, engines can be opened to military power immediately. In dives, the limit hand of the speed indicator should not be exceeded. As the airplane approaches its limiting Mach number, a mild buffet starts at the tail. In some planes, a very mild nose down or tuck under tendency will develop, which will become less evident as the limiting Mach number is approached. The elevator trim tabs should be used with caution at high speeds. The aileron roll is smoothly executed with the aileron boost system operating. Displacement is limited according to the airspeed and altitude combinations shown on the acceleration charts in the flight handbook. The airplane will not perform a satisfactory snap roll because auto-rotation ceases after 1/4 to 1/2 turn. In making vertical turns, wing-overs, and chandelles, the pilot is also guided by the maximum permissible acceleration according to airspeed and altitude. Loops and Immelman turns should be entered with at least 350 knots. In inverted flight, the oil supply to the engines is limited to approximately 10 seconds. Longer periods of inverted flight should not be attempted. Normal flight operations for best range and best endurance call for single-engine flight. To shut down an engine in flight, throttle all the way aft. It will be necessary to trim the airplane to compensate for off-center thrust. Let the engine windmill until tailpipe temperature is below 233 degrees centigrade. Do not windmill for more than 30 minutes at engine speeds above 20% RPM, and do not windmill when air temperature is less than -40 degrees. Fuel off on this engine. Engine master switch off. This closes the air inlet duct door or butterfly and stops windmilling. It is important to be sure that there is no burning in the engine before you close the butterfly. The recommended low-speed cruise condition is with one engine operating at normal rated power. Single engine operation at altitudes below 20,000 feet will result in increased range and endurance. The best air starts can be made below 25,000 feet. If above 25,000 feet, windmilling RPM must not exceed 16% RPM prior to light off. Indicated airspeed should be approximately 200 knots. With the dead engine throttle in the off position, turn the engine master switch on to open the air inlet duct door. As the engine begins to windmill and reaches 12 to 16% RPM, turn the fuel on. Start igniting and ease the throttle forward opposite. When light off is obtained, use the throttle during acceleration to control the tailpipe temperature. The approach letdown is best made with engines throttled back and speed brakes extended, losing altitude between 200 to 250 knots indicated airspeed. Avoid prolonged engine operation between 68 to 76% RPM because of critical stresses in the compressor. The nose will be well down, giving the pilot good visibility of the traffic and area below. At pattern altitude, you'll want at least 500 pounds of fuel aboard to give a margin of safety for a possible wave-off. Enter the pattern with engines throttled back, speed brakes out, and speed approximately 2 airspeed. Shoulder harness locked and armament switches off. Let's look at the overall pattern for approach in the Banshee. Enter the pattern with engines throttled back, speed brakes out, and at the landing pattern altitude. Enter the downwind leg, and at 174 knots, lower the landing gear. As the airplane slows down below 165 knots, lower the flaps. There will be very little trim change because of the flap-operated Banshee, which moves the stick ahead as flaps go down. Retract the speed brakes immediately and hold about 125 knots on the downwind leg. The speed on the base leg is 120 knots. On the final approach, when you are sure you can make the runway, retard the throttles to idle, and with normal landing load conditions, come over the end of the runway at 110 knots. Let's follow through on the approach and checklist. We enter the pattern with engines throttled back, using the speed brakes to slow down. Into the downwind leg, and at 174 knots, landing gear down. At 165 knots, flaps down, speed brakes closed, canopy open. Double-check landing gear indicators down. Finish the downwind leg at 125 knots, slowing to 120 knots on the base leg. Over the end of the runway at 110 knots. Set the yaw stabilizer switch to off position immediately prior to touchdown. In the final approach, the airplane is flown to the ground with the tail down, but not in a stall landing attitude. After touchdown, use the speed brakes to slow down. When you know you are down to stay, move the stick back to hold the nose up as long as possible. As the elevators lose their grip, the nose will rock over gently to the three-point attitude. Then brakes can be used strongly and evenly to control the landing run. In a crosswind landing, normal landing technique is used. On the tricycle landing gear, the airplane will roll straight with a minimum of rudder and brake steering. As a carrier aircraft, the Banshee has proved itself. The pilot will find, however, that his responsibilities do not cease when he gets the cut. The airplane must be controlled in speed, attitude, and position all the way through to the rollback of the arresting gear. In the event of a wave-off or incomplete landing attempt, advance the throttle smoothly to 100% RPM and climb at 115 knots indicated airspeed. Immediately retract the landing gear. At a safe altitude, raise the flaps and fly in the clean condition until ready to attempt another landing. About 240 pounds of fuel are required for an immediate go-around. In securing the aircraft after flight, chocks should be placed fore and aft of the main wheels and inlet screens installed. To shut down the engines, advance engine speed to 60% momentarily, then move the throttles to the off position. Make sure throttles are all the way aft. Fuel off both engines. Master radio switch off. Battery generator switch off. Aileron boost off. Engine master switches off. This procedure will leave the duct doors open. After the engines have cooled for several minutes, put the battery generator switch in battery generator position, and when duct doors have closed, return switch to off. Air inlet duct guards should be inserted and the airplane tied down. In this film, you have seen how the Banshee is handled in taxiing and flight. Reference to your flight handbook will help you perfect your understanding of this airplane. In this film, we will consider what to do in case of some of the emergency situations that can arise in the F2H2. These include engine failure, system failure, fire, forced landing, ditching, and emergency escape. If the engine failure occurs before becoming airborne, the airplane may swerve slightly but can be easily controlled. Chop the throttles on both engines, turn the fuel off, and stop straight ahead. In the event of engine failure of one engine immediately after takeoff, you want to work fast. Retract the landing gear, raise the flaps to 1/2 or less. Jettison external fuel tanks if containing fuel. Climb straight ahead at the airspeed which gives the maximum angle of climb. On the dead engine, shut off the throttle and fuel. If both engines fail on takeoff, cut throttles and fuel on both engines. Retract the landing gear, lower full flaps, turn off the battery generator switch, and land straight ahead. In a double flameout at possible engine recovery altitudes, you'll need all the electrical power you can get for starting. So pull all electrical load off the line, including inverter circuit breaker if flight is VFR. In single-engine landing, plan the approach carefully to avoid a possible wave-off. If space permits, use slightly higher speed and only 1/2 to 1/4 flap to improve the performance of the airplane in the event of a wave-off. If you have to take a single-engine wave-off, retract the gear and gain speed before starting to climb. Good pilot technique can compensate for failure of any flight system in the aircraft. This includes failures of generator, battery, fuel transfer, landing gear, aileron boost, and cabin pressurization systems. In case of generator failure, one generator will sustain operation. If the warning lights show that both generators have failed, immediately turn off all equipment not essential to flight. The battery will operate the primary bus or main circuits for only a few minutes. If necessary to operate any items on the other buses, release the guard and move the power switch to emergency or battery-only position. Battery failure in flight de-energizes the primary bus only when the landing gear control is in the down position. If the battery fails in flight, lower the landing gear normally. Immediately pull the landing gear circuit breakers and then re-energize the bus by placing the landing gear control in the up position. Bear in mind that flight with gear down is restricted to below 174 knots. Failure of one tip tank to transfer fuel will be indicated by a no reading on the transfer indicator and a gradually increasing heaviness of that wing. Turn both transfer switches to stub tank and trim as necessary. If there is much difference in the weight between tanks, experiment to find the landing approach speed that will give you good lateral control. When you're on the deck, keep the nose wheel down. Use the speed brakes and wheel brakes to slow you down. If the landing gear does not indicate locked down after normal operation, pull the power circuit breaker for the gear that indicates down. Raise gear handle and pull out all landing gear circuit breakers. Put gear handle in down position and pull smartly aft about 3 inches until it locks. Leave it locked and down. The main landing gear will free fall into down position, and the air cylinder will push the nose gear to the down position. Check the indicators to see that the gear is down. If the aileron boost system fails on either or both ailerons, turn the aileron boost switch to off and use the trim tabs and stick to regain normal straight and level flight. If cabin pressurization fails or noxious fumes are present in the cockpit, operate the emergency ventilation control on the right console. If fumes are present, use 100% oxygen. In case of any apparent failure of the oxygen system or symptoms of anoxia, immediately turn the safety pressure lever and descend below 10,000 feet. Oxygen will be supplied under pressure. If the oxygen regulator becomes inoperative, use the bailout oxygen bottle to below 10,000 feet. Engine fire in flight will be indicated by the fire warning lights on the main instrument panel. On the affected engine, close the throttle and turn the fuel off. An engine will help extinguish the flames. In case of electrical fire or short circuit, turn the battery generator switch off. Reset the popped circuit breaker and then turn the battery generator switch on again. If the circuit breaker pops again, leave it alone. In the event of a forced landing due to complete engine failure, the pilot's safety depends on doing the right things at the right time. If the tip tanks contain fuel, jettison them. Issue Mayday call on the radio and turn on the emergency IFF. Canopy locked open. Check safety belt and harness. Fuel off. Throttles closed. Battery generator switch off. Govern the glide to have too much altitude instead of too little at touchdown. When you're sure you can make the runway, turn battery generator switch to battery and lower the wheels and flaps. Carry 4 to 5 knots extra speed for landing. Pop the speed brakes after touchdown and use the wheel brakes during the runout. Turn the battery generator switch to off. Normally, a wheels-up landing should be made on short runways, cow pastures, or other suitable terrain. For ditching, follow the same general procedures as for forced landing with these differences. If the tip tanks are empty, for extra buoyancy. If full, jettison them. The landing gear should be up for water landings, and the landing should be made in a fully stalled attitude. If the wind is light and swells are heavy, land parallel to the swells. Otherwise, land into the wind. Check shoulder harness locked and personal gear disconnected. Leave the airplane as quickly as possible. There are 2 methods of opening the canopy in emergencies. The exterior canopy control, when pulled aft, actuates an air control valve to move the canopy aft. The canopy drive gear box will hold the canopy open against a 40G forward-acting load. The canopy may be also opened by pulling aft on the interior canopy control. Here is the procedure to use the ejection seat. Reduce airspeed if possible. Pull either or both pre-ejection handles up and aft. This forms knee braces, jettisons the canopy, and arms the seat. Put your feet full aft in the stirrups. Pull the ball handle of the oxygen bailout bottle if at altitude. It is important that you sit erect in the seat with spine straight and head pressed against the headrest. Do not tip your head back, however. Grasp the face curtain handles with your elbows close to your body and pull the face curtain until fully extended. Pulling the face curtain fires the catapult. The upward movement of the seat disengages personal gear. As soon as the seat is falling free, after at least a 5-second delay, pull the ripcord on your parachute. If escape is accomplished at high altitudes, parachute opening should be delayed so that you will free fall to a comfortable altitude. In this film, you have seen emergency procedures for the F2H2 Banshee. You will agree that the best time to consolidate these procedures in your mind is before the emergencies arise. This film on the F2H2 Banshee will show the operation of some of the important aircraft systems. These include the flight systems pertaining directly to the flight of the aircraft. The fuel and oil systems and the electrical systems will be covered. The film will also show some of the operational equipment. The tricycle landing gear, including the wheel well doors, is electrically operated. Emergency landing gear extension is provided by an emergency position of the landing gear control handle. In this position, the landing gear actuators are disengaged. The main gear falls free to the down position, and the nose gear pneumatic emergency air cylinders push the nose gear into the down position. The main wheels are equipped with hydraulic disc-type brakes with an air boost system which provides increased braking force. The brakes on each wheel are independent and may be applied individually or together. Wings are folded and unfolded electrically. The wing pin locks are manually operated through a mechanical linkage. The wing flaps are electrically operated and may be stopped at any desired position. The flaps are connected by a bungee to the control stick so that when flaps go down, the stick is moved ahead. The flaps will blow up at speeds in excess of 165 knots. Speed or dive brakes are electrically operated and can be used at any flight speed to slow down the airplane. The speed brakes are controlled by a toggle switch on the right-hand throttle grip. All trim tabs are electrically operated. A combination trim and anti-balance tab is installed on the rudder and is controlled by a nose left, nose right toggle on the left console aft of the throttle quadrant. Aileron and elevator trim tabs are controlled by a four-way switch on the control stick hand grip. Aileron control is assisted by a hydraulic boost system with a separate pump and motor for each aileron. The switch on the left console controls both aileron boost systems. Forward on the right console, you will find the yaw stabilizer switch, which automatically corrects for directional instability of the airplane. A limit switch at the main landing gear scissors automatically disconnects the system on the ground. The test position bypasses the landing gear disconnect so that the system can be checked while taxiing. The fuel system for this aircraft operates by pressure feed to the engines. The center fuselage tank feeds directly to the fuel system manifold. The forward and aft fuselage tanks transfer to the center tank through gravity feed lines with submerged fuel pumps to transfer the last 900 pounds. The two stub wing tanks transfer through a submerged pump to the center tank. Tip tank fuel is transferred to the center tank by air pressure supplied by the engine compressors. The total fuel in overload fighter condition is 1,277 gallons, or 7,662 pounds of aviation gasoline, or approximately 8,200 pounds of JP3. Indicators on the pilot's forward sub-panel show when fuel is being transferred from the stub and tip tanks. The transfer switches are located on the left console aft of the throttles, and the fuel quantity, fuel flow, and fuel totalizer indicators are forward of the throttles. The oil system provides lubrication to the accessory gearbox and main bearings regardless of the attitude of the airplane. To do this, the oil reservoirs located in the wing operate under 4 pounds per square inch pressure at the tank, while high-pressure oil lines operate under pressures ranging from 5 to 90 pounds per square inch, depending on engine speeds. The airplane is equipped with a 24-volt DC single-wire electrical system powered by one 24-volt 34-ampere-hour battery and two 28-volt 300-ampere engine. Direct current power distribution is divided on 3 buses. The primary bus supplies DC power for equipment essential to safe flight and operates the inverter to power the AC flight instruments. With battery generator switch in battery generator position and both generators inoperative, the primary bus only is energized. With both generators out, placing the electric power switch in battery only position will energize the secondary bus to power other equipment. A third bus, the monitor bus, powers the pilot's suit heater and gun camera heater. In addition, the IFF destructor and canopy control circuits are energized when the battery is installed regardless of the position of the battery generator switch. The AC power system consists of a main inverter and a standby or alternate inverter which supplies 3-phase AC when DC current is available. The airplane is equipped with an automatic cabin pressurization and temperature control system which uses compressed air from the engine compressor sections. When the ventilating foot heat position, pressurization air enters the cabin in the region above the pilot's feet. When the control is in defrost position, all the incoming air is directed to the windshield and canopy. Cabin pressure control is automatically controlled, selected by the toggle switch on the pressurization control panel. With the switch in normal position, at from sea level to 5,000 feet, cabin altitude follows the actual altitude. From 5,000 to 13,000 feet, cabin altitude remains at 5,000 feet. Above 13,000 feet, the cabin pressure is held at 3.3 pounds above the outside pressure. the switch in combat position, cabin pressure is the same as normal position up to 35,000 feet. From 35,000 to 50,000 feet, the regulator adjusts to a combat ratio of 2.3 psi pressure differential. Above 50,000 feet, a differential pressure of 1.3 psi is maintained. When the cabin temperature control switch is in the automatic position, a cabin thermostat controls the mixing to maintain the temperature selected at the thermostat. When the switch is held at either hot or cold position, the automatic controls are bypassed. Emergency ventilation control on the right console provides ram air ventilation, opens the dump valve, and closes the pressurization shutoff valve. The oxygen equipment in the airplane is the automatic positive pressure diluter demand regulator type. The system operates on a full charge of approximately 1850 psi to supply positive pressures of oxygen for operational flights up to equivalent cabin altitudes of 43,000 feet. There is provision for emergency descent from 50,000 feet in case of loss of cabin pressurization. Additional pressure and flow indicators are mounted forward on the left console where they can be more easily read by the pilot. The anti-blackout system, or G-suit, air from the compressor section of each engine. The valve opens at 1.75 G. When the control is set in the low position, 1 pound per square inch of air is provided for every 1 G increase thereafter. When the control is in the high position, the unit provides 1 1/2 pounds per square inch per G of acceleration. Pressing down on the top of the valve manually inflates the suit. Electronic equipment in the F2H2 will be covered briefly in this film. For details and operating information, consult your flight handbook. The master control panel contains the radio master switch and the volume control. The VHF transmitter receiver AN-ARC1 gives two-way voice communication on a line-of-sight range. The radio compass AN-ARN6 can be used over a 250-mile range for homing compass or position finding, as well as for normal range reception. The navigation receiver AN-ARR2A completes the list of communication gear aboard. The IFF receiver transmitter AN-APX6 is used for identification purposes. This unit is fitted with a destructor switch for use if in danger of falling into enemy hands. Controls for the radar set AN-APG30 are located on the left console forward of the fire control panel. This equipment provides automatic and continuous range to the fire control system. For the radio altimeter AN-APN1, the power switch is at the indicator. The range switch controls operations from 0 to 400 feet in the low range and 400 to 4,000 feet in the high range. The altitude limit switch is located on the left console after the throttle. The airplane is armed with 4 20mm forward-firing guns with 150 rounds of ammunition per gun. The guns are charged pneumatically and fired electrically. Gun control switches are on the main instrument panel. The armament master switch must be on before the guns can be fired. The gun control switches for inboard guns, respectively, have 3 positions. To charge the guns, move the gun control switches from off to safe. When ready to fire, the switches must be in the ready position. The guns may be fired in pairs or in salvo. The gun trigger is on the control stick grip. The gun camera operates automatically when the armament master switch is on and the trigger is squeezed. On the wings, there are launchers for 8 rockets or 100-pound bombs. 4 250-pound bombs may be carried, or 2 500-pound bombs, as well as certain combination bomb and rocket loads. Bomb and rocket controls consist of bomb and rocket master switch with safe and ready positions, an arming switch with nose and tail, and safe position, and a station selector. The bomb and rocket release switch is on the control stick. If the station selector is placed in number 1 position, launcher station 1 is fired. Selector position 2 fires station 7. Selector 3 fires station 3. Selector 4 fires station 5. As the selector is rotated in order, stations 8, 2, 6, and 4 are fired. Rockets or bombs may be fired in pairs by originating the fire order in positions 5 to 8 inclusive. Pairs are fired symmetrically from outboard to inboard as the station selector is rotated from 5 to 8. This airplane employs the fire control system Mark 6 Mod 0, which is a lead computing reflector sighting system. It incorporates a Mark 8 Mod 0 gyroscopically controlled sight. The manual ranging control is on the left-hand throttle. The fire control system may be used in air-to-air gunnery operations or for air-to-ground rocketry and may be used in conjunction with radar ranging. This film has covered some of the systems and operational equipment on the F2H2 Banshee. Your ability to get high operational efficiency out of this versatile and effective airplane will be improved by further study of your flight handbook and current technical bulletins.